we'll do, again, some trials of some of these estimates in class so that you can get the feeling of what it's like to make estimates about length or area or volume. It turns out that if we're thinking about length, there's almost a perfect correspondence between the actual difference and the perceived difference. But if we think about area, we tend to underestimate area, and volume, we tend to way underestimate volume. So that's why 3D charts, like from Excel, are looked down upon by people who are in data visualization. It's because we tend to way underestimate the differences between things of two different volumes. And this is an example of Weber's law, which is that differential sensitivity is inversely proportional to the size of the components of the difference, and relative differential sensitivity remains the same regardless of size. Weber's law is something that has been shown to work for things like length and area and volume. And then I've seen some visualizations like this one is by Lane Harrison, Remco Chang, and some other co-authors, where they were trying to see if correlation followed that same kind of pattern. So they had people look at different correlations and try and say, which one is more correlated between these two. And they were trying to focus on that just noticeable difference thing that we talked about with color, but just noticeable difference for correlation. If you want to try out seeing how good you are at assessing correlation, you could go to this website, guessthecorrelation.com, and there's a game where you can play. It turns out that humans are not very good at perceiving correlation. So that was one of the results from this study. And then they were able to rank these different ways of visualizing correlation. So this was, again, a perceptual experiment, sort of like the Cleveland-McGill experiments, and I think that they found that the scatter plot was maybe the best overall, at least if it was a positive correlation, and maybe it's harder for people to make the assessment if it's a negative correlation. Another one that is good is the parallel coordinates plot, and on and on. So there's different ways to visualize it, and I think that they said that these perceptual differences for correlation followed Weber's law. Interestingly, there was a follow-up paper that used the same data because this was reproducible research. They published their data and their code, and someone did a reanalysis of the data where they came up with a slightly different conclusion. So it's maybe not as exact as Weber's law would suggest. So just to wrap up kind of the overview of some of these perceptual choices. Let me move my video down a little bit so you can read this better up there. In terms of perception, probably the best is position on a common scale, then position on an unaligned scale, and down, volume is the worst one. Curvature is not very useful. And so when I talk about mappings, these are often the mappings that I talk about, like position on a common scale or position on the x-axis, and the length, something like that. So when you're assessing visualizations, you might want to consider how good they will be for humans' perception in terms of humans' ability to judge differences. But again, there are these kind of rules, but then there are very good reasons to break the rules, depending on your audience or the goal that you have. I'd just like to wrap up by thinking a little bit about bar charts and histograms as visualization types. And maybe I need to move my video even one more time. Put myself over in this corner. So bar charts are a way to visualize a categorical variable, and they map some value, either the sum for a particular category or some other value. In this case, it's the average inches of precipitation that each of these cities get. So that is mapped to position along a common scale. In this case, it is the x-axis, the length of that bar or that position along the scale. And it could, you could rotate the bars and have them going up, so it would be on the y-axis. And then the name of the category is being mapped to the other axis. So those are the mappings that I think about there. And often a bar chart is an aggregation of data. So if I had an original data table like this, and then I was interested in knowing how many diamonds fall into each of these different color categories, I would need to move from the overall table, which I think has like 1 million rows, to this summarized table. where I see that there's 6,775 in color D, and on and on. And then I could turn that into my bar chart where I'm mapping that count to, in this case, the y-axis, or that length, that position on that common scale, and then the x-axis is the color. So that's maybe the simplest type of visualization, a visualization of one categorical variable. We have a very similar visualization, which is a histogram, and this also uses just one variable, but it's for a numeric variable. And I don't remember if I've shown you this histogram essay before, but this is a tool that I developed with a collaborator to help explain how histograms work, and maybe I'll just go there. This is an essay about histograms with my collaborator, Erin Lunzer, and if you want to go look at it and read it, you certainly can. But I also just like it as something that I can walk through in a video like this with you. So the idea with a histogram is that you gather your data and maybe you put it in order. So again, this is position along a common scale. We're sort of putting them in order. Right now, I haven't actually put them on the scale. I've just ordered them. But then I could put them along the number line. So put those dots down into those positions on the common scale, and I can see how far apart they are, or how close they are to one another. And then I could think about this with other types of data sets. So if I had many repeated values, maybe I would stack them up. And now I'm starting to use height as a mapping. But it is very explicit. It's not aggregated. It's just one dot means one data point. And then if I had even more data, as with this example, things would pile up. But I'm starting to see more of a gestalt here, kind of the overall distribution of the data. And these are just little toy data sets. Oftentimes you have thousands or millions of data points, and so it's not possible to put all those dots on the plot. You actually run out of pixels at some point on your computer screen. So aggregation is a useful technique to be able to summarize a data set. So with that, we would break the data into bins and then count up how many values fall into each of those bins. And now we've got this, height of the bars, or position along a common scale. So the y-axis is the number of items that fall into that category. And then the x-axis, it's not just the categories exactly, it's like the whole number line, but we are seeing those breaks for each of the bins. And then the thing that I find really interesting about histograms is that they are parameterized. And so if you choose a different bin break algorithm, you'll get a slightly different aggregated gestalt, sort of look at the whole data set. So I could bump those bin offsets over just a little bit, leaving the bin width the same, but looking at slightly different bin offsets. And then this overall sense of my data is going to change slightly. I think I can see the sort of bimodality no matter what offset I pick, but sometimes it gets more smoothed out and it looks more sort of uniform in one piece or another. And then you can also change the way things look if you vary the bin width. So if you aggregate more and more or less and less, you're going to see different shapes again. So that parameter, it's not really a mapping, but it's an aggregation on your data that's making a difference in the plot that you see, or the gestalt. And then this doesn't work as well on the iPad. It works pretty well on the computer, but you can do a sweep of values and look at a sort of histogram cloud. Let's see if I can do it with my iPad. There we go. So here's a sweep of values, and I could see, one histogram really darkly, or I could see them all kind of as a cloud. And these are different versions. Let's see if I can turn back on the highlighting slightly. Oh my goodness, nope. Try again. Turn back on the highlighting a little bit, and then I could step through. Okay, so here's one of the histograms in my histogram cloud. Here's another one. And I can see these are different bin widths, so I'm sweeping over width, and I'm getting this kind of, this fuzzy histogram or histogram cloud. If I wanted to, I could also sweep over offset. So I could leave the width the same, but sweep over offset, and then look at these different plots as well. And I think I need to turn on plot as densities to have that look nice in terms of the comparisons. I'd be happy to talk about this visualization or this interactive essay with you. I think that this gets very detailed at the end and maybe isn't appropriate for all audiences, but I think at this level where you're thinking about statistics and data visualization kind of deeply, I think that you probably could understand all of the complexity down at the bottom of this essay. So I'd be interested in talking about it with you. So I think we've talked about a lot here. I think the most important things are, of course, these visual attributes that we have to play with. And then again, we may end up breaking the rules here, but knowing the effectiveness of different mappings and the way that they can impact people based on perception. Those are probably the most important takeaways.